Do you know how to exponentiate this matrix? How to explicitly find e to the power LT? For an arbitrary 2 by 2 matrix this happens to be possible, not so for an arbitrary 3 by 3 or 4 by 4 or n by n matrix, but in the case of a 2 dimensional matrix, just 2 dimensional matrix, arbitrary 2 by 2 matrices, this turns out to be fairly easy and simple to do. And let me spend a few minutes, digress and do this. We will look at some examples and then you get some practice doing this. You see, the difficulty is that if you took a matrix L equal to A, B, C, D and you want to find L squared, L cubed and so on, this can be extremely tedious, and the reason it becomes tedious is because this is shorthand for A times 1 0 0 1 plus B times 0 1 0 0 plus C times 0 0 1 0 plus D times 0 0. This thing here is shorthand for that, and these are the 4 basis matrices, the natural basis for 2 by 2 matrices. In the language of linear algebra, that is the natural basis, and this is what you mean by a matrix. Okay. However, the problem arises, sorry, this should be a 0 here. The problem arises because these matrices, their commutation properties are not trivial. So if you take 2 of these matrices and ask what is the product and what is the product in the reverse order, they are not necessarily equal to each other, and you can see that this gets fairly complicated as you go along. So what one would like to do is to change the basis to a better basis where the mutual commutation properties between the basis vectors, basis matrices, is a little simpler, and these are the famous Pauli matrices. So you have of course the unit matrix which is 1 0 0 1, you have the first matrix sigma 1 equal to 0 1 1 0, sigma 2 equal to 0 minus I 0, sigma 3 equal to 1 0 0 minus 1. These are called the Pauli matrices. Are you familiar with these matrices? Yes? Some of you are, some of you aren't. Never mind, it is actually quite simple. These matrices have very interesting properties, they are called the Pauli matrices. And they are linearly independent of each other, and it is an elementary statement to say that any arbitrary 2 by 2 matrix can be expanded uniquely as a linear combination not of just these 4 basis matrices but of these 4 basis matrices. So you could write any arbitrary 2 by 2 matrix as a linear combination of I, sigma 1, sigma 2 and sigma 3. Okay. That is a simple exercise, I leave it to you to do that, because start with this A, B, C, D and insist on writing it in this form. So write this thing as this same matrix, write it as alpha naught I plus alpha 1 sigma 1 plus alpha 2 sigma 2 plus alpha 3 sigma 3, and you see immediately that alpha naught, alpha 1, alpha 2, alpha 3 are linear combinations of A, B, C, D, and you can solve for one set in terms of the other and vice versa uniquely. So this immediately shows that you could expand a matrix in this basis as well. There is no restriction that the alphas have to be real or anything like that, because as you see one of the basis matrices itself has got I out there. The advantage of this basis is that these matrices are Hermitian, they are equal to their complex conjugate transposes. That is not true here. On the other hand, these matrices have that symmetry property, and it is also a simple exercise to show, and I am going to give this as a problem set to work out all the properties of these guys. Sigma I squared equal to the unit matrix. The square of every one of these matrices is equal to the identity matrix. Moreover, sigma I sigma j plus sigma j sigma I equal to 0 if I not equal to j. They anti-commute with each other. and that is a very powerful property for what we want to do, because if you want to write e to the power LT, you write e to the LT equal to e to the alpha naught I plus, let me call it alpha I sigma I with a summation over this index I implied. It looks almost like a vector, alpha dot sigma, except you must remember that the components alpha 1 2 3 need not be real numbers, could be complex numbers in general.